Hello, dear listener. Where are you right now? Perhaps in your bed with soft sheets caressing your skin, or maybe sitting in your favorite armchair with a cup of tea still steaming beside you. What time is it where you are? Is it night? Is it early morning? How do you feel at this moment? Relaxed? Curious? Ready for an extraordinary journey? Regardless of where you are, I invite you to close your eyes for a moment and come with me to one of the most extraordinary places on our planet. Imagine yourself now in the vast frozen plains of the Arctic, where the silence is so profound that you can hear your own heart beating against your ribs. The air is sharp, pure, crystalline. Each breath awakens something ancestral and wild within you. Above, the night sky stretches infinitely, like a velvet black mantle embroidered with sparkling diamonds. The stars twinkle with an intensity you've never seen in cities, each point of light telling stories of unimaginable distances and times lost in the cosmos. You're in the middle of nowhere and everything at the same time. And then something magical begins to happen. On the northern horizon, a thin line of greenish light appears, shy at first, as if testing whether it's welcome in this cosmic theater. Gradually, it intensifies, undulating gently like ethereal silk moved by invisible winds. The color becomes more intense, an emerald green that seems to have a life of its own, pulsing and dancing against the absolute darkness. This is the aurora borealis, also known as the polar aurora, or as the Nordic peoples poetically called it, the northern lights. Have you ever thought about this? How is it possible that the sky itself transforms into a cosmic painter's canvas, creating a work of art that rivals any human creation? How is this celestial dance born that has fascinated humanity since the dawn of civilization? What you're witnessing is not just a dazzling visual spectacle, it's the result of an extraordinarily complex cosmic dance involving our star, the sun, our planet Earth, and the very fundamental laws of physics. It's a story that began billions of years ago and continues to unfold every second, right above our heads, at the tenuous frontier between our world and the vast cosmos. Tonight, on this special evening we'll spend together, I want to take you on a journey of scientific discovery and poetic contemplation. Let's unveil together the most intimate secrets behind this phenomenon that has captured human imagination since our ancestors first raised their eyes to the night sky and wondered about those mysterious lights dancing on the horizon. Have you ever wondered why auroras appear mainly at the Earth's poles? Why do their colors vary between hypnotic greens, delicate pinks, and mystical violets? How do modern scientists manage to predict with days of advance when they will appear? And more importantly, what can this dance of lights teach us about the fundamental nature of the universe and our precious place within it? Prepare yourself for an experience that combines the most rigorous science with the natural poetry of the cosmos. We'll explore not only how an aurora borealis is born, but also why it represents one of the most beautiful and revealing manifestations of the deep interconnection between all elements of our solar system. This is a story about subatomic particles that travel 93 million miles through the vacuum of space, invisible but powerful magnetic fields that silently protect us, and atmospheric gases that transform into pure light when touched by stellar energy. Our journey will take us from the nuclear depths of the sun to the confines of Earth's atmosphere, passing through the mysteries of the magnetosphere and the secrets of quantum physics. We'll discover how auroras are simultaneously local phenomena, specific lights in the sky above, particular observers, and cosmic events connected to the fundamental rhythms of our star and our planet. To truly understand how an aurora borealis is born, we need to begin our journey at the place where everything starts, the burning heart of our sun. Imagine this star not as the golden, tranquil disk we see during the day, but as an incredibly active and dynamic nuclear furnace, a cosmic power plant where unimaginable temperatures of 27 million degrees Fahrenheit constantly transform matter into energy. In the solar core, every second that passes, 600 million tons of hydrogen are converted into helium through the process of nuclear fusion. To give you an idea of the magnitude of this transformation, the energy released is equivalent to the simultaneous explosion of 100 billion hydrogen bombs. Can you imagine such magnitude? It's an atomic dance so intense that it creates pressures and temperatures capable of overcoming the electrical repulsion between atomic nuclei and forcing them to fuse. This nuclear energy, born in the heart of the sun, begins an epic journey that can take up to 1 million years to reach the solar surface. The photons created in fusion reactions zigzag through the solar layers, being constantly absorbed and re-emitted by atoms in a random process that scientists call a random walk. It's as if each particle of light were a lost traveler in a gigantic labyrinth, taking eons to find the exit. But what particularly interests us for understanding auroras are the most dramatic and spectacular events that occur on the solar surface, solar storms. Visualize the chromosphere and corona of the sun as turbulent oceans of superheated plasma, where magnetic fields with intensities thousands of times greater than Earth's magnetic field intertwine, break, and reconnect in explosions that defy our understanding. During these storms, scientifically called coronal mass ejections or CMEs, something truly extraordinary happens. Billions of tons of electrically charged particles, mainly protons and electrons, are catapulted into space at velocities that can reach 1,250 miles per second. Have you ever thought about this? It's as if the sun were constantly breathing charged particles into the cosmos, creating a solar atmosphere that extends far beyond Pluto's orbit. These particles form what we call the solar wind, a constant and invisible stream of plasma that spreads in all directions from our star. But the solar wind isn't uniform. It constantly varies in intensity, velocity, and density, depending on magnetic activity on the solar surface. During periods of high activity, the sun can produce even more intense eruptions, creating true tsunamis of energetic particles that cross the solar system. Imagine each of these particles as a tiny cosmic messenger, carrying with it not only kinetic energy, but also precious information about conditions on the sun. They transport interplanetary magnetic fields, creating a complex and dynamic structure that extends throughout the solar system. They don't follow straight trajectories, on the contrary. They're influenced by constantly changing magnetic fields, creating spiral currents that extend for millions of miles. The sun operates in activity cycles lasting approximately 11 years. During solar maxima, the number of sunspots, eruptions, and coronal mass ejections increases dramatically. It's as if our star had periods of more tranquil sleep alternating with periods of frenzied activity. Currently, we're ascending toward the maximum of solar cycle 25, which means the coming years will be particularly rich in solar storms and, consequently, spectacular auroras. Have you ever wondered how these microscopic particles, born in the nuclear depths of the sun, manage to travel 93 million miles through the vacuum of space? They face an extraordinary journey, navigating through interplanetary magnetic fields, being accelerated and decelerated by shock waves, interacting with the interplanetary medium in complex ways we've only recently begun to understand. When these particles finally approach Earth, a journey that takes between 1 to 5 days, depending on their initial velocity, they bring with them all the energy and information accumulated during their epic journey. But here they encounter a majestic and protective obstacle: Earth's magnetic shield, our magnetosphere, which determines the final fate of these solar particles and, ultimately, whether they'll be able to create the aurora borealis spectacle. Now, I invite you to imagine something truly extraordinary and invisible. A gigantic shield that completely surrounds our planet, extending tens of thousands of miles into outer space. This shield isn't made of metal, rock, or any tangible material we could touch. It's composed entirely of magnetic force lines that emanate from the depths of Earth's core and create a colossal protective bubble around our world. This is Earth's magnetosphere, one of the most important and simultaneously invisible phenomena that make life possible on Earth. To understand how this extraordinary magnetic shield works, we need to take an imaginary journey to the depths of our planet, more than 3,000 miles beneath your feet. In Earth's outer core lies a turbulent ocean of liquid iron in constant motion. This molten metal, heated to temperatures exceeding 7,200 degrees Fahrenheit, hotter than the sun's surface, flows in complex and hypnotizing patterns, driven by Earth's rotation and convective movements caused by the gradual and inexorable cooling of the planet. These majestic movements of liquid iron function like a gigantic dynamo, generating colossal electrical currents that, in turn, create Earth's magnetic field. It's an elegantly self-regulated process that has been working for billions of years. Movement generates magnetism. Magnetism influences movement, and movement maintains magnetism in a perpetual cycle of creation and maintenance. Have you ever thought about the elegance of this system? It's as if Earth itself were a living magnetic generator, pulsing with energy since its birth 4.6 billion years ago. Have you ever wondered why our planet has this unique magnetic capability among nearby rocky planets? Mars, for example, lost its global magnetic field approximately 4 billion years ago, leaving its atmosphere completely exposed to devastating solar winds. Venus never developed a significant magnetic field. Mercury has only a weak and asymmetric field. Earth is genuinely special in this aspect, and this uniqueness is fundamental to the existence of auroras. Earth's magnetic field isn't uniform or static. It's a dynamic and three-dimensional structure of fascinating geometric beauty. Its force lines emerge from the magnetic South Pole, curve gracefully through space in majestic arcs, and converge again at the magnetic North Pole. Imagine them as invisible strings of a cosmic harp that extend from Earth's interior to tens of thousands of miles in space, creating a region of magnetic influence we call the magnetosphere. But here's a crucial detail. The magnetic poles don't coincide with the geographic poles. The magnetic North Pole is currently located in the Canadian Arctic archipelago, approximately 250 miles from the geographic pole, and is constantly moving currently at a speed of about 30 miles per year towards Siberia. This difference between magnetic north and geographic north is fundamental to understanding aurora geography. When charged particles from the solar wind, traveling at velocities of hundreds or thousands of miles per second, encounter this magnetosphere, something absolutely fascinating happens. The vast majority of them are elegantly deflected, like water flowing smoothly around a stone in a crystalline stream. The particles follow magnetic force lines, being directed away from the equatorial and middle regions of the planet. It's as if Earth were constantly combing the solar wind, separating and directing these energetic particles with mathematical precision. Earth's magnetosphere has a fascinating and asymmetric shape. On the side facing the sun, it's compressed by constant solar wind pressure, assuming an almost hemispheric form that extends to approximately 40,000 miles from Earth. On the side opposite the sun, it elongates, forming a magnetic tail that can extend for millions of miles into space, farther than the Earth-Moon distance. But here's the absolutely crucial detail for auroral birth. Earth's magnetic field isn't a perfect and impenetrable barrier. In the polar regions, magnetic field lines converge and plunge directly into Earth's atmosphere, creating magnetic gates or funnels through which some of the most energetic solar particles manage to penetrate. It's as if there were invisible magnetic tunnels connecting outer space directly to the upper atmosphere in the Arctic and Antarctic regions. Can you visualize this extraordinary cosmic geometry? Imagine a huge invisible magnetic water drop, with Earth suspended in the center, being constantly bombarded by a furious wind of particles coming from the sun. Most of these particles slip harmoniously along the surface of the drop, but some manage to follow the force lines that converge at the poles, penetrating the atmosphere like special guests at an exclusive cosmic party. This elegant magnetic architecture perfectly explains why auroras occur preferentially in approximately circular rings around the magnetic poles, regions that scientists call auroral ovals. During periods of low solar activity, when particle bombardment is moderate, these ovals remain contracted at higher latitudes. But during intense solar storms, when particle flow increases dramatically, the ovals expand significantly, allowing auroras to be seen at much lower latitudes, sometimes reaching even temperate regions of the planet, where millions of people who rarely have this opportunity can witness the spectacle. We're now reaching the most crucial and magical moment of our entire journey, the extraordinary instant when solar particles, after completing their epic 93 million-mile journey through outer space and navigating through the complex three-dimensional labyrinth of Earth's magnetosphere, finally encounter their final destination, our atmosphere. Imagine yourself floating gently about 60 to 200 miles above Earth's surface in the region scientists call the thermosphere. Here you would technically be in space, but there would still be enough atmospheric molecules to create a fascinating and luminous interaction. It's at this tenuous and special frontier between solid Earth and infinite cosmos that the miraculous birth of Aurora Borealis occurs. Solar wind particles that manage to penetrate through the magnetic gates of the poles arrive at this atmospheric region charged with colossal kinetic energy, some traveling at velocities up to 600 miles per second. To give you a dimension of this velocity, they could circle the Earth 3 complete times in just 2 minutes. Carrying all the energy accumulated during their long journey from the Sun, they approach atmospheric gas molecules like extremely energetic microscopic projectiles seeking atomic targets. At this extraordinary altitude, our atmosphere is already so rarefied that gas molecules float isolated like tiny islands in an ocean of nearly perfect vacuum. The density is approximately 1 trillion times lower than at sea level. Here we find mainly isolated oxygen atoms and nitrogen molecules, with much smaller concentrations of other gases like helium and hydrogen. These atmospheric particles are separated by relatively enormous distances on an atomic scale. It's as if they were solitary stars navigating through intergalactic space. When an energetic particle from the solar wind, say, an electron accelerated to relativistic velocities, collides with an oxygen atom or nitrogen molecule in the upper atmosphere, something absolutely extraordinary and fundamental happens. The solar particle transfers part of its kinetic energy to the electrons of atmospheric atoms, instantly elevating them to much higher energy levels than their normal states. It's like throwing a stone into a perfectly calm lake. All the stone's kinetic energy transfers to the water, creating ripples that propagate in concentric circles. But atoms and molecules have a fundamental and inviolable characteristic of nature. They absolutely don't like to remain in high-energy states for prolonged periods. It's against their fundamental physical essence. Thus, in fractions of a second, sometimes in nanoseconds, the excited electrons relax, returning to their original and more stable energy levels. And here's the luminous secret of auroras. When returning to the ground state, these electrons must release all excess energy in the form of visible light. Have you ever thought about the mathematical and poetic elegance of this quantum process? Each individual photon of light you see dancing in auroras is the direct result of a single microscopic quantum event, an electron jumping from one specific energy level to another. Multiply this by trillions and trillions of simultaneous interactions occurring every second, and you have the complete scientific explanation for the ethereal curtains of light that dance majestically in polar skies. But why do different atmospheric gases produce such distinct and characteristic colors? The answer lies in the fundamental principles of quantum physics and the unique electronic structure of each chemical element. Each atom has an absolutely specific energy signature, like a luminous fingerprint, that identifies it unequivocally in the universe. When electrons of oxygen atoms return from excited states to the ground state, they emit mainly green-yellow light with a very specific wavelength of 557.7 nanometers. This is the characteristic green color that dominates approximately 80% of all visible auroras. If oxygen excitation is even more intense, during particularly powerful solar storms, atoms can emit deep red light with a wavelength of 630 nanometers. Molecular nitrogen, in turn, produces a completely different luminous spectrum. Its excited molecules can emit bright blue and intense violet light, creating the rarest and most spectacular aurora hues. Have you ever wondered why green is by far the most common color we observe in auroras? It's simply because atomic oxygen is the most abundant gas at the specific altitude where most auroral collisions occur, and its electronic transition to green is particularly efficient and probable. The intensity and brightness of auroras depend directly on the quantity and energy of solar particles that manage to reach Earth's atmosphere. During moderate solar storms, auroras are visible but relatively weak. But during extreme magnetic storms, particle bombardment is so dense and energetic that auroras become extraordinarily bright, sometimes visible even during nights with a full moon, competing in luminosity with moonlight itself. It's as if Earth's atmosphere temporarily transformed into a giant natural lamp, powered directly by the sun's nuclear energy. Now that we understand the fundamental mechanism of how auroral light is created, let's dive into one of the most hypnotizing and poetically beautiful aspects of this phenomenon, the extraordinary chromatic richness that paints polar skies with a palette that rivals nature's most exuberant works of art. Each specific color you observe dancing in auroras tells a precise scientific story about altitude, particle energy, types of gases involved, and local atmospheric conditions. Imagine yourself again in that vast frozen Arctic plain, observing a particularly spectacular aurora unfolding majestically above your head. The color that most captures your attention is that bright and hypnotizing emerald green, undulating like ethereal curtains of luminous silk against the black velvet of the night sky. This iconic green color, which statistically dominates about 80% of all visible auroras worldwide, has a very specific and absolutely fascinating scientific origin. The green light of auroras is born precisely when energetic electrons from the solar wind collide with oxygen atoms at altitudes between 60 and 200 miles above Earth's surface. In this specific atmospheric region, pressure is approximately 1/1,000,000th of the pressure you feel at sea level, so incredibly rarefied that oxygen atoms can remain in excited electronic states for relatively long periods in atomic terms, about 0.7 seconds, before finally releasing their accumulated luminous energy. When an oxygen atom is impacted by an energetic electron from space, one of its orbital electrons instantly jumps to a very specific higher energy level. This is what physicists call a forbidden state, not because it's physically impossible, but because the transition back to the ground state takes an exceptionally long time in atomic timescales. During this quantum waiting period, the atom carries the excess energy like a perfectly charged microscopic battery, awaiting the right moment to discharge. When the excited electron finally quantum decides to return to its original energy state, it releases a photon with a wavelength of exactly 557.7 nanometers, located precisely in the green-yellow region of the visible electromagnetic spectrum. Have you ever thought about the impressive mathematical precision of this color? Each specific shade of green your eyes capture is the direct result of an absolutely precise quantum transition, as mathematically exact as the musical note produced by a violin string of perfectly determined length and tension. But aurora's chromatic spectacle extends far beyond the dominant green. When solar particles are particularly energetic, during especially intense solar storms that occur at peaks of solar activity, they manage to penetrate deeper into the magnetosphere's structure and reach even higher atmospheric altitudes, between 200 and 250 miles above Earth's surface. In this higher region where atmospheric density is even more extremely low, excited oxygen can produce a completely different and majestic color, a deep and ethereal red. This red light from high auroras is produced by a completely different quantum electronic transition of the same oxygen atom, releasing photons with a wavelength of 630 nanometers. It's a significantly rarer and more precious color in auroral nature, generally visible only during extremely intense auroras and severe geomagnetic conditions. When present, this red emission creates an ethereal and majestic crown at the top of lower green curtains, as if Earth's atmosphere itself were being crowned by an incandescent cosmic ruby diadem. Molecular nitrogen contributes its own distinctive and spectacular colors to the auroral palette. At relatively lower altitudes of the thermosphere, between 50 and 75 miles, where the atmosphere still maintains a slightly higher density, excited nitrogen molecules can produce bright electric blue and intense violet. These colors are considerably less common than oxygen's green because they require much more specific and extreme conditions. Extraordinarily energetic solar particles capable of penetrating to these relatively lower and denser altitudes. Have you ever wondered where those absolutely dazzling pink and magenta tones we sometimes observe in the most spectacular auroras come from? These exotic and rare colors arise from the natural optical combination of different simultaneous atomic emissions. Deep red from oxygen at high altitudes optically mixing with bright blue from nitrogen at low altitudes, creating intermediate tones that seem to have been carefully painted by a cosmic artist with refined aesthetic sensibility. It's literally a color mixing happening in the sky itself, where each individual photon carries the specific chemical signature of the atom that created it through fundamental quantum processes. The relative intensity of each specific color depends not only on the initial energy of incident solar particles, but also on local atmospheric density at each specific altitude. In atmospheric regions where density is slightly higher, collisions between particles are statistically more frequent, but simultaneously more absorption and scattering of produced light occurs. It's a dynamic and delicate equilibrium that determines precisely which colors manage to propagate through the atmosphere and effectively reach our eyes on Earth's surface. During particularly spectacular and rare aurora, you may be lucky enough to observe a true vertical chromatic cascade, ethereal reds at the highest altitudes, dominant greens at medium altitudes, and electric blues at the lowest altitude, creating a natural vertical spectrum that extends for hundreds of miles through Earth's atmosphere. It's like witnessing quantum physics itself painting a giant vertical rainbow in the night sky, where each color represents a specific altitude and a distinct atomic process. Now that we've unveiled the mystery of auroral colors, it's time to explore another equally fascinating and scientifically revealing aspect: the extraordinary and geometrically complex forms that these lights assume in the cosmic theater of the night sky. Auroras aren't simply random or diffuse patches of colored light floating chaotically in the atmosphere. They follow very specific and organized structural patterns that directly reflect the three-dimensional invisible architecture of Earth's magnetic field and the real-time dynamics of the solar wind. Imagine yourself patiently observing a typical aurora beginning to form on the Arctic horizon. Initially, you might perceive a smooth, diffuse, and relatively weak arc appearing timidly at the northern horizon line, like a delicate curve of pale light that seems to rest gently on the boundary between Earth and sky. This is what scientists call a quiet auroral arc, the most basic and fundamental manifestation of the auroral phenomenon. At this initial stage, the aurora seems so tranquil and apparently static that you could easily mistake it for an artificially illuminated cloud or a common atmospheric phenomenon. But then, gradually and almost magically, something extraordinary begins to happen before your amazed eyes. The arc begins to intensify progressively, and you can observe much more defined and dynamic structures emerging from the initial apparent simplicity. Well-defined vertical rays of colored light appear, as if someone were pointing gigantic and invisible spotlights from outer space itself toward Earth's surface. These luminous rays follow with absolute mathematical precision the invisible lines of Earth's magnetic field, extending vertically for dozens of miles through the upper atmosphere. Have you ever thought deeply about why auroras assume these specific and organized geometric forms? The answer lies in the fundamental principles of charged particle physics in magnetic fields. Energetic particles from the solar wind, upon penetrating Earth's magnetosphere through polar magnetic funnels, are literally forced to follow magnetic field lines like microscopic beads sliding along invisible but absolutely rigid wires. They cannot move freely in any direction they might wish. They are elegant and disciplined prisoners of three-dimensional magnetic geometry. As geomagnetic activity intensifies, the initial auroral arc can fragment dramatically, creating what specialized scientists call discrete aurora. Imagine undulating luminous curtains that move and dance gracefully in the sky, each meticulously following its own individual magnetic force line. It's as if Earth's magnetic field itself, normally completely invisible to our senses, were becoming visible through auroral light, revealing its complex three-dimensional structure that remains eternally hidden under normal conditions. During moderate to high-intensity auroras, you may witness the majestic formation of auroral bands, organized strips of light that extend horizontally from east to west across vast sky expanses, like luminous bridges connecting distant horizons. These bands can have hundreds or thousands of miles of horizontal extension, while simultaneously maintaining widths of only a few hundred meters, creating an impressive linear geometry that challenges our habitual and limited perception of atmospheric space. One of the most spectacular and rare manifestations is the auroral corona, a visually dazzling phenomenon where individual light rays seem to converge geometrically to a focal point. located exactly above the privileged observer. It's like finding yourself at the architectural center of a gigantic cosmic cathedral, with luminous pillars of emerald green and ruby red extending in all possible directions to a majestic focal point in the celestial zenith. This extraordinary visual configuration occurs when the observer positions themselves exactly below a magnetic field line that's being intensely bombarded by a concentrated flow of energetic solar particles. Auroras can also assume hypnotizing spiral forms, creating what visually appears to be cosmic whirlpools of pure light slowly rotating in the night sky. These spiral structures are particularly fascinating from a scientific viewpoint because they directly reflect the dynamic and complex interaction between different particle flows with varying energies and subtle local variations of Earth's magnetic field. It's like observing luminous hurricanes of light, but instead of being composed of wind and water vapor, they're formed by subatomic particles and invisible electromagnetic fields. Have you ever wondered why some auroras seem to pulse rhythmically like cosmic heartbeats? This pulsating aurora is a particularly intriguing phenomenon that occurs when there are regular and predictable temporal rhythmic variations in the arrival of solar particles to Earth's atmosphere, creating a completely natural stroboscopic visual effect. Imagine the sky itself breathing light rhythmically, with intensities that increase and decrease in regular and predictable cycles, sometimes perfectly synchronized with low-frequency electromagnetic waves that invisibly traverse the magnetosphere. During extreme magnetic storms, events that occur only a few times per decade, auroras can assume completely chaotic, dynamic, and unpredictable forms. You may witness auroral substorms, sudden and dramatic light explosions that rapidly expand across the entire sky, creating luminous patterns that change so quickly it's physically difficult for human eyes to completely follow the temporal evolution. It's like watching cosmic fireworks filmed in slow motion, where each luminous explosion instantly reveals new geometric patterns and previously unobserved structures. The apparent speed with which these auroral forms move across the sky is equally impressive and illusory. Although they appear to move relatively slowly when observed from Earth's surface due to the perspective effect of great distance, some auroral structures move in reality at velocities of hundreds or thousands of miles per hour in the upper atmosphere. It's an optical illusion similar to observing commercial aircraft at high altitude that appear to move slowly to a terrestrial observer, but are actually flying at supersonic velocities. There's also a less dramatic but scientifically important category called diffuse auroras, smooth and homogeneous mantles of light that cover large sky areas without well-defined geometric structures. These visually less impressive auroras are actually statistically more common than discrete and structured ones, but frequently go unnoticed by casual observers because their luminosity is too low to create a dramatic visual impact. They reveal the presence of a constant and spatially uniform bombardment of relatively low-energy particles, creating a subtle but persistent background illumination. During particularly favorable geomagnetic conditions, different types of auroras can coexist simultaneously in the same sky, creating a complex visual overlay of diffuse arcs, discrete curtains, vertical rays, and spiral structures all dancing in perfect choreographic harmony. It's a spectacle that combines the geometric precision of mathematics with the poetic fluidity of dance, where each luminous movement reflects fundamental physical processes occurring at the invisible frontier between our planet and the infinite cosmos. Aurora borealis don't constitute a constant and immutable spectacle that we can observe whenever we wish. They obey extraordinarily complex cosmic rhythms that mirror the intrinsic activity cycles of our star and the seasonal and rotational variations of our planet. Understanding these multifaceted temporal patterns is like deciphering a sophisticated cosmic code that intimately connects our terrestrial experience to the fundamental rhythmic pulses of the entire solar system. Imagine the sun as a gigantic cosmic heart pulsing with its own characteristic rhythm, but on time scales that completely transcend common human experience. The fundamental solar cycle, discovered and documented more than 150 years ago by German astronomer Heinrich Schwab through meticulous sunspot observations, has an average duration of approximately 11 Earth years. During this extraordinarily long period, Solar magnetic activity grows gradually and systematically until reaching a spectacular intensity maximum, then decreases slowly and progressively to an almost complete minimum, to then inexorably begin a new cycle of growing activity. During solar maxima, which typically last 2 to 3 years, the number of visible sunspots, violent magnetic eruptions, and coronal mass ejections increases dramatically, often by factors of 10 or 100 times compared to periods of minimal activity. These solar maxima send much more intense and frequent waves of energetically charged particles toward Earth and all other planets in the solar system, creating ideal conditions for spectacular and frequent auroras. Have you ever thought what it would be like to experience auroras during different specific phases of this long-term solar cycle? During deep solar minima, which can persist for several consecutive years, auroras become genuinely rare and relatively weak events, confined almost exclusively to geographic regions closest to the magnetic poles. It's as if the cosmos were gently whispering instead of singing with full voice. Auroral ovals contract geographically, and observers situated at middle latitudes can spend entire years without witnessing a single visible aurora. But when we progressively approach solar maximum, the situation transforms completely and dramatically. Solar storms become much more frequent, intense, and long-lasting events, sending dense swarms of extremely energetic particles that significantly expand auroral ovals to much lower geographic latitudes than normal. During these privileged periods of high solar activity, auroras can be regularly observed as far south as France, northern Spain, northern United States, or even more equatorial regions, latitudes where it would normally be completely impossible to observe any auroral manifestation. There are also much faster and perceptible temporal cycles that govern auroral activity on human timescales. Solar rotation, with a period of approximately 27 Earth days, creates recurrent and predictable temporal patterns in the arrival of solar particles to Earth. Specific active regions of the Sun, like persistent coronal holes or long-lasting sunspot groups, can remain pointed directly at Earth for several consecutive days, creating concentrated auroral seasons that repeat cyclically every complete solar rotation. Within even smaller and more immediately perceptible timescales, auroras follow absolutely fascinating and scientifically significant daily rhythms. There's a well-documented phenomenon known as magnetic midnight, not necessarily coincident with local clock midnight, when auroral activity systematically tends to reach its maximum peak of intensity and spectacularity. This specific time is directly related to the complex three-dimensional geometry of Earth's magnetosphere and the way it dynamically interacts with the solar wind during Earth's 24-hour daily rotation. Have you ever wondered why certain specific times of year are consistently more favorable for observing intense and spectacular auroras? There's an intriguing and well-established seasonal pattern known scientifically as the equinoctial effect. During the spring and autumn equinoxes, approximately March 20th and September 22nd, when Earth's rotation axis is geometrically perpendicular to the imaginary Earth-Sun line, the magnetosphere's spatial configuration becomes significantly more favorable for efficient penetration of energetic solar particles. During these special equinoctial periods, even with only moderate levels of solar activity, auroras can be statistically more intense, long-lasting, and visible at lower geographic latitudes than during other times of the year. Winter and summer in polar regions, paradoxically, tend to be times of lower statistical auroral activity, despite Arctic winter offering ideal observation conditions with extremely long nights and naturally dark skies for consecutive months. There are still temporal variations on much smaller scales. The fascinating auroral substorms that can last a few specific hours, creating sudden, dramatic, and visually spectacular intensifications of luminous activity. Imagine patiently observing a relatively calm and stable aurora when, suddenly, and without warning, the entire sky explodes in a dynamic spectacle of light that moves, dances, and evolves with surprising speed and incomparable beauty. These substorms function like atmospheric storms, but occurring specifically in the invisible magnetosphere. Scientists have discovered that these auroral substorms follow a typical and predictable temporal pattern, an initial phase of silent and gradual growth, followed by an explosive phase that can last 30 minutes to an hour, and finally a slow and progressive recovery phase. It's as if Earth's magnetosphere were systematically charging magnetic energy from incident solar particles and then releasing it instantaneously in a concentrated explosion of visible auroral activity. There's also the scientifically fascinating phenomenon of recurrent auroras, specific luminous patterns that repeat with almost mathematical precision every exact 27 days, directly reflecting long-lasting and persistent structures in the solar corona that maintain their orientation relative to Earth. Experienced and dedicated observers can sometimes predict with surprising precision the return of particularly spectacular auroras, knowing that a specific active region of the Sun will return to point directly at Earth after completing a complete solar rotation. And there are still ultradiurnal cycles, variations that occur within minutes or even seconds. During particularly active and dynamic auroras, you can observe undulations that visibly propagate along auroral curtains like waves in a gigantic cosmic theater curtain. These luminous waves reflect high-frequency oscillations in particle currents or rapid instabilities in magnetic fields that generate dynamic and hypnotizing visual structures. Now that we understand the complex temporal rhythms of auroras, it's time to explore in detail their cosmic geography, the specific and precise locations on our planet, where this celestial light spectacle is most likely to occur with frequency and intensity. The geographic distribution of auroras reveals fundamental and fascinating truths about the three-dimensional structure of Earth's magnetic field and about how our planet dynamically interacts with the surrounding space environment. Imagine a detailed world map viewed from above the North Geographic Pole, with Earth appearing as a rotating blue-green disk surrounded by the infinite darkness of outer space. If you could meticulously draw on this map all the auroras that occur during a complete year, based on satellite observations and terrestrial stations, you would discover something absolutely remarkable. They don't distribute randomly or uniformly across the planetary surface, but form two almost perfectly circular and symmetric rings around the magnetic poles, north and south. These are the famous auroral ovals, specific geographic regions where auroras are statistically most frequent, intense, and spectacular. The auroral oval of the Northern Hemisphere, where aurora borealis that so fascinate observers worldwide are born, is not centered on the North Geographic Pole, as many people might intuitively imagine. Instead, it's centered on the magnetic North Pole, which is currently located in the Canadian Arctic archipelago, approximately 250 miles distant from the geographic pole. This crucial geographic distinction is absolutely fundamental for understanding where auroras are most likely to occur and with what intensity. Have you ever thought carefully about why specific places like Fairbanks in Alaska, Yellowknife in Canada, Tromsø in Norway, Reykjavik in Iceland, or Murmansk in Russia are considered privileged destinations and internationally recognized for aurora observation? These cities and regions are positioned approximately at the ideal latitude of the auroral oval, between 65 and 72 degrees of magnetic latitude. It's as if they were geographically situated in the impact zone most statistically favorable for energetic solar particles. But auroral geography is significantly more complex and interesting than simply a matter of simple magnetic latitude. Magnetic declination, the angular difference between true magnetic north and geographic north, varies dramatically around different longitudes of the terrestrial globe, creating a distorted and asymmetric geometry that favors certain specific regions over others. In North America, for example, the auroral oval extends geographically further south than in Asia or Europe, scientifically explaining why auroras can occasionally be observed as far south as the northern United States, while they're rarely seen at equivalent latitudes in Europe or Asia during periods of low solar activity, such as during deep solar minima. The auroral oval contracts geographically, concentrating auroras at the highest latitudes closest to the magnetic poles. It's as if Earth were metaphorically pulling its luminous curtains closer to the poles, making them visible only to observers in remote Arctic regions. But during intense magnetic storms, the oval expands dramatically and can almost double in size. allowing auroras to be seen at latitudes as low as 50 degrees or less, bringing the cosmic spectacle to densely populated regions inhabited by millions of people who rarely have the extraordinary opportunity to witness this phenomenon. There's also the fascinating scientific concept of privileged magnetic longitude, certain specific longitudes where, due to the particular three-dimensional configuration of Earth's magnetic field, auroras tend to be statistically more intense and spectacular. The nighttime sector of the magnetosphere, approximately between 9 p.m. and 3 a.m. in magnetic local time, is particularly favorable for the development of extraordinarily bright and structured auroras. It's during these specific hours that the complex magnetosphere geometry allows maximum efficient penetration of energetic solar particles. Have you ever wondered about subtle geographic differences in the visual appearance and structure of aurora? In northern Canada and central Alaska, where Earth's magnetic field is almost perfectly vertical, auroras tend to appear as luminous curtains extending directly from east to west, creating an impressive linear geometry. In Scandinavia, where magnetic field lines have a slightly different angular inclination due to the magnetic pole's position, auroras can assume subtly distinct spatial orientations, creating visual patterns characteristic and recognizable of each specific geographic region. Local terrestrial topography also influences aurora observation significantly and surprisingly in ways many observers don't consider. Elevated mountainous regions can physically block part of the crucial northern horizon view for auroral observation, but simultaneously can elevate the observer above low cloud layers and fog, offering cleaner and more transparent skies. The famous Norwegian fjords, for example, create protected natural corridors, free from urban light pollution, where auroras can be observed with exceptional clarity, contrast, and definition. Light pollution from modern cities has created a new artificial auroral geography, an important distinction between locations where auroras can technically occur and locations where they can truly be appreciated and photographed. Even moderately intense auroras can be completely invisible in the heart of large urban centers, where artificial brightness from city lights completely masks this delicate natural spectacle. This modern reality has created a contemporary exodus of dedicated aurora hunters, who regularly travel to remote and geographically isolated regions in search of truly dark and pristine skies. There are also significant seasonal variations in auroral geography directly related to the 23.5-degree inclination of Earth's rotation axis. During the Arctic winter, when polar regions are plunged into polar darkness for consecutive months, absolutely ideal observation conditions are created: extremely long nights and naturally dark skies. Paradoxically, the Arctic summer, with its midnight sun phenomenon, makes it completely impossible to visually observe any aurora, despite them continuing to occur normally in the upper atmosphere, invisible due to constant sunlight. During the spring and autumn equinoxes, when Earth-Sun geometry is optimized for solar particle penetration, certain specific geographic regions experience a statistical increase in the frequency and intensity of observable auroras. These preferential auroral seasons can last several weeks and are well known by experienced observers, who plan their observation expeditions to coincide with these geographically and temporally privileged periods. The movement of the magnetic North Pole itself is creating gradual changes in auroral geography. As the magnetic pole continues its migration towards Siberia at about 30 miles per year, the optimal viewing zones are slowly shifting. Locations that were prime aurora viewing spots decades ago may become less favorable, while new regions are emerging as better vantage points for future aurora watchers. One of the most fascinating and practically revolutionary aspects of modern aurora science is our growing ability to predict with surprising accuracy when and where they will occur, completely transforming aurora observation from a matter of pure luck and coincidence into an almost exact and reliable science. This extraordinary predictive capability allows dedicated enthusiasts to plan specific trips in advance, scientists to prepare sophisticated instruments to capture data during particular events, and critical technological systems to protect themselves against potentially damaging effects of geomagnetic storms. Imagine an impressive global network of technological sentinels constantly watching our star with a vigilance that never sleeps. Specialized satellites like SOHO, Solar and Heliospheric Observatory, SDO, Solar Dynamics Observatory, and STEREO, Solar Terrestrial Relations Observatory, observe the Sun continuously, 24 hours a day, 365 days a year, meticulously monitoring its turbulent surface in multiple electromagnetic wavelengths to detect the first signs of growing magnetic activity. When a significant solar eruption or coronal mass ejection is detected by these space observatories, a coordinated cascade of information is immediately transmitted to specialized prediction centers scattered around the world. Dedicated scientists instantly analyze these observations, using sophisticated computational models to determine whether the solar storm is specifically directed toward Earth and what its expected intensity will be when it reaches our planet. The scientific prediction process begins with detailed analysis of the specific characteristics of the observed solar storm. Researchers carefully examine the velocity of ejected particles, their spatial density, propagation direction, and most importantly, the three-dimensional orientation of the interplanetary magnetic field they carry with them. Have you ever thought how scientifically impressive it is that we can determine, several days in advance, whether a particle cloud located tens of millions of miles away will interact efficiently with our planetary magnetic field? The fundamental key to accurate predictions lies in what scientists call BZ orientation, specifically the south-north component of the interplanetary magnetic field transported by solar particles. When this component points south, negative BZ, it can reconnect very efficiently with Earth's magnetic field, functioning like a key that perfectly opens Earth's magnetic lock, allowing much larger quantities of solar particles to penetrate the magnetosphere and create intense and spectacular auroras. Specialized centers like AIN-OAA Space Weather Prediction Center in the United States, the UK Met Office Space Weather Operations Center, and Brazil's National Institute for Space Research use extraordinarily sophisticated computational models to track these particle clouds during their epic Earth-Sun journey. These models can calculate arrival time with typical precision of a few hours, allowing them to issue specific alerts about when auroral conditions should begin, what their expected intensity will be, and approximately how long they should last. Modern auroral prediction goes far beyond simply detecting solar storms directed at Earth. Scientists have developed sophisticated, quantitative indices that numerically classify the level of geomagnetic activity. The most famous and widely used is the KP index, which varies from 0, magnetically quiet conditions, to 9, extreme geomagnetic storm. Each specific KP level corresponds statistically to a particular geographic extension of the auroral oval, allowing prediction not only of when there will be auroras, but also precisely to what geographic latitude they will potentially be visible. Have you ever wondered how popular cell phone apps manage to send surprisingly accurate notifications about imminent auroras? These applications connect in real time to global geomagnetic monitoring networks, continuously processing data from strategically distributed terrestrial magnetometers that detect characteristic fluctuations in the local magnetic field that precede and accompany auroral activity. When these instruments register the specific magnetic signatures of a developing auroral substorm, alerts are instantly sent to thousands of interested observers around the world. Local and regional prediction is even more sophisticated and accurate. Coordinated networks of high-sensitivity automated cameras, like the impressive Themis network in North America and the Miracle network in Scandinavia, capture complete night sky images every few seconds during the entire Arctic darkness season. These images are automatically processed by artificial intelligence algorithms that can identify different types of auroral structures, track their movement and intensity in real time, and predict their likely evolution in the coming hours, based on historical patterns and current geomagnetic conditions. There's also long-term prediction based on well-established solar cycles. Knowing that we're currently ascending toward the maximum of solar cycle 25, which should occur approximately between 2024 and 2026, scientists can confidently predict that the coming years will be particularly favorable for intense, frequent auroras visible at lower geographic latitudes than normal. It's like having a cosmic calendar that tells us when to expect the decade's best auroral shows. The most advanced prediction models also incorporate seasonal, geographic, and local atmospheric factors. Specialized algorithms automatically calculate the darkness conditions necessary for visual observation at different latitudes and times of year, combining geomagnetic activity predictions with precise astronomical data about solar and lunar positions, and even local weather forecasts about expected cloud cover. One of the most impressive tools of modern prediction is the ability to predict the photographic visibility of auroras with modern digital cameras. Using detailed data about the sensitivity of different types of digital sensors and established nighttime photography techniques, some specialized services can predict not only whether auroras will be visible to the naked eye, but also whether they'll be detectable by long exposure photographs, dramatically expanding observation and documentation opportunities for amateur and professional photographers. Advanced prediction systems now incorporate machine learning algorithms that analyze decades of historical data to identify subtle patterns that human forecasters might miss. These AI systems can recognize complex relationships between solar wind parameters, Earth's magnetic field orientation, and seasonal factors to provide probability-based forecasts that are becoming increasingly accurate. The integration of citizen science has also revolutionized prediction accuracy. Thousands of aurora photographers and observers worldwide now contribute real-time reports through smartphone apps, creating a global network of ground truth data that helps refine and validate satellite-based predictions. Aurora borealis completely transcend their function as a dazzling visual spectacle. They constitute a unique and irreplaceable natural laboratory, where we can study fundamental principles of physics under conditions that are completely impossible to replicate in any terrestrial laboratory. Each luminous curtain that gracefully dances in the Arctic sky carries precious scientific information about physical processes that govern not only our planet and solar system, but potentially the entire observable universe. Imagine having the opportunity to study plasmas with temperatures of millions of degrees Celsius, magnetic fields of colossal intensities, and individual particles accelerated to velocities approaching the speed of light. All of this happening naturally and continuously in our own planet's upper atmosphere. Auroras offer us exactly this extraordinary scientific opportunity, functioning as a natural cosmic particle accelerator that operates uninterruptedly, 24 hours a day, 7 days a week, offering experimental data that perfectly complements controlled laboratory experiments. Through meticulous and multidisciplinary study of auroras, scientists have unveiled fundamental secrets about how electrically charged particles behave when subjected to intense and variable magnetic fields. The complex interactions that create the different observable auroral forms, arcs, curtains, spirals, coronas, are direct visible manifestations of fundamental physical principles that operate on scales extending from the subatomic nucleus to gigantic galactic structures. Have you ever thought deeply that by observing an aurora, you're literally witnessing the fundamental laws of physics in direct action? Not in abstract mathematical equations or computational graphs, but in all their visual glory dancing majestically before your amazed eyes? The scientific study of the intimate connection between solar activity and terrestrial auroral manifestations completely revolutionized our understanding of what researchers call space weather. We discovered that the apparently empty space between planets is not a sterile and silent vacuum, but rather an extraordinarily dynamic and complex environment filled by invisible magnetic fields, energetic particles in constant motion, and electromagnetic waves of multiple frequencies. Auroras function as sophisticated cosmic weather stations that help us monitor, understand, and predict these space conditions in real time. This deepened scientific understanding has enormous and critical practical implications for our modern technological civilization. The same intense solar storms that create spectacular and visually dazzling auroras can simultaneously cause catastrophic failures in artificial satellites, severe interruptions in global communication systems, interference in GPS navigation systems, and even blackouts in terrestrial electrical networks affecting millions of people. Detailed study of auroras has taught us to predict and proactively protect ourselves from these potentially destructive events, transforming a phenomenon originally purely scientific and aesthetic into a genuine matter of national security and critical infrastructure. Have you ever wondered how auroras historically helped us understand the structure and composition of Earth's upper atmosphere? Before the era of artificial satellites and spaceflights, auroras literally constituted our only observational window for studying atmospheric regions between 50 and 300 miles altitude, a region inaccessible by traditional weather balloons, but still too low for satellites in stable orbit. The specific altitude where different auroral colors appear taught us fundamental details about the vertical distribution of different atmospheric gases and about how atmospheric density and composition varies systematically with height. Auroras also scientifically revealed the existence of colossal electrical currents flowing invisibly in the upper atmosphere, the phenomenon we call the auroral electrojet. This natural atmospheric current can transport literally millions of amperes of electricity, creating its own secondary magnetic field detectable by sensitive magnetometers installed on Earth's surface. It's literally a giant river of electricity flowing silently in the sky, completely invisible to our direct senses, except for the luminous auroras that mark its path through the atmosphere. Meticulous study of temporal aurora variations, from decade-long cycles to second-long fluctuations, has taught us fundamental aspects about the complex dynamics of Earth's magnetosphere. We discovered that our protective magnetosphere isn't a static and immutable magnetic structure, but rather an extraordinarily dynamic system that constantly reconnects, spatially reorganizes, stores magnetic energy, and releases this accumulated energy in sudden explosions. Auroral substorms are direct visible manifestations of these explosive magnetic energy release processes. Terrestrial auroras also served as a fundamental laboratory for studying and understanding physical phenomena occurring on much larger scales elsewhere in the universe. The same fundamental physical processes that create auroras on Earth, charged particle acceleration, magnetic reconnection, atomic excitation, and light emission, also operate on other solar system planets, on other stars, in interstellar nebulae, and even in distant galaxies. Jupiter and Saturn possess auroras much more intense and spectacular than terrestrial ones, powered by their extraordinarily powerful magnetospheres and volcanically active moons. Through detailed and sophisticated spectral observations of terrestrial auroras, using high-resolution spectrometers, scientists have mapped not only the precise chemical composition of Earth's upper atmosphere, but also developed and refined observational techniques now routinely used to study atmospheres of extrasolar planets orbiting other stars. Aurora light, when analyzed with sophisticated spectral instruments, reveals not only which specific gases are present in the atmosphere but also their temperatures, densities, movement velocities, and electronic excitation states. Auroras have taught us fundamental lessons about the geological and magnetic history of Earth's magnetic field over timescales extending thousands of years. Historical variations in aurora intensity, frequency, and geographic location over centuries have provided critical scientific evidence about how Earth's magnetic field has gradually changed in the past, including dramatic events like complete magnetic pole reversals, which occur approximately every 200,000 to 300,000 years. Detailed historical records of auroras observed at geographically unusual latitudes tell us about extreme solar storms that occurred before the era of modern scientific instruments. Multidisciplinary study of auroras also revolutionized our understanding of the dynamic and complex Sun-Earth connection. We discovered that our planet is literally immersed in the Sun's extended atmosphere, the gigantic heliosphere, and that changes in solar activity propagate through the solar system like waves in a cosmic lake. Auroras are the most sensitive, immediate, and visually obvious indicators of these intricate interplanetary connections. Modern auroral research using coordinated networks of terrestrial and space instruments has revealed that Earth's magnetosphere can function as a giant natural antenna, capturing and amplifying low-frequency electromagnetic waves originating both from the Sun and from deep interstellar space. These waves can subtly influence auroral patterns and potentially even affect terrestrial biological systems in ways we're only beginning to understand. Our in-depth exploration of terrestrial auroras naturally leads us to a fascinating and cosmically scoped scientific question. Do other celestial bodies in our solar system also experience these extraordinary luminous spectacles? The answer is a definite and enthusiastic yes, and auroras from other worlds reveal even more spectacular, diverse, and scientifically revealing aspects of this truly universal phenomenon that connects all magnetized planets to their stars. Imagine embarking on an extraordinary cosmic journey to Jupiter, the gaseous colossus that gravitationally dominates our solar system with its impressive mass equivalent to more than 300 Earths. If you could magically position yourself on one of its icy moons, perhaps Europa or Ganymede, and direct your gaze toward the Jovian poles, you would witness auroras that make the most spectacular terrestrial ones seem like modest birthday candles compared to industrial spotlights of colossal power. Jupiter's auroras are literally hundreds or thousands of times brighter than their terrestrial counterparts, creating permanent and intense rings of ultraviolet light around its magnetic poles. What makes Jovian auroras so extraordinarily spectacular and energetically powerful? Jupiter possesses the strongest and most extensive magnetic field of all known planets in the solar system, approximately 20,000 times more intense than Earth's magnetic field. This truly colossal magnetic field captures and accelerates energetic particles not only from the distant solar wind, but also from its own geologically active moons, especially Io, which continuously ejects tons of sulfur, oxygen, and other elements through its extremely active volcanoes. Have you ever thought about the poetic possibility of auroras directly fueled by volcanoes from distant moons, creating a luminous symphony that connects geological activity to atmospheric spectacles? Saturn, the elegant ringed planet, presents another absolutely fascinating type of aurora with unique characteristics in the solar system. Its auroras possess a remarkable scientific peculiarity. They pulse rhythmically in perfect synchronization with mysterious radio waves emitted by the planet itself, creating a kind of cosmic heartbeat that connects electromagnetic phenomena to luminous manifestations. The particles responsible for these Saturnian auroras come both from the solar wind and from the spectacular ice geysers of the moon Enceladus, which continuously ejects water vapor and ice particles into the surrounding space. But perhaps the most scientifically intriguing and geologically revealing auroras are those observed on Mars, our red planetary neighbor. This fascinating world lost most of its global magnetic field approximately 4 billion years ago, during a catastrophic period of planetary core cooling, but still preserves fossil magnetic fields, specific geographic regions where ancient rocks crystallized and preserved residual magnetism from the era when Mars possessed an active magnetosphere. When energetic particles from the solar wind interact with these localized and fragmented magnetic fields, they create auroras in isolated and dispersed patches, like luminous islands randomly scattered across the planetary surface. Their fragmented and intermittent auroras, luminous ghosts of a planetary magnetosphere that no longer exists. Venus, our nearest neighbor and often called Earth's sister planet, presents an even more peculiar and scientifically challenging case. Without a significant magnetic field of its own due to its extremely slow rotation, Venus develops auroras when the solar wind interacts directly and violently with its dense upper atmosphere. It's as if the solar wind itself were literally painting directly on the Venusian atmosphere, creating diffuse auroras that spread over large areas of the planet's night side without the characteristic geometric organization of magnetized planets. And then we have the moons, celestial bodies that reveal completely unique aspects of the auroral phenomenon. Europa, Jupiter's icy moon that harbors a subsurface ocean of liquid water, develops delicate oxygen auroras when particles from Jupiter's intense magnetic environment strike its extremely tenuous water vapor atmosphere. Ganymede, the largest moon in the solar system, is the only known natural satellite to have its own miniaturized magnetic field, creating small-scale auroras that simultaneously reveal the presence of a subsurface ocean of salty water. Have you ever wondered if distant stellar systems might have auroras? Recent astronomical discoveries have revealed that some brown dwarfs celestial objects that are too large to be planets, but too small to sustain nuclear fusion like true stars, produce auroral emissions detectable by sophisticated terrestrial radio telescopes. These stellar auroras are millions of times more energetically powerful than any known planetary aurora, suggesting that similar phenomena may occur on unimaginably larger cosmic scales. The ice giants of the outer solar system, Uranus and Neptune, also possess their characteristic and scientifically revealing auroras. Uranus, with its rotation axis practically perpendicular to the orbital plane, creates auroras that move completely differently from any other known planet, rotating dramatically as the planet spins. Neptune, the most distant of the gas giants, develops auroras powered by particles, so extremely energetic that they create emissions at wavelengths we don't observe anywhere else in the solar system. Comparative study of planetary auroras teaches us that this phenomenon is truly universal and fundamental. Wherever there simultaneously exists a magnetic field, an atmosphere, even if extremely tenuous, and a source of energetic particles, auroras can and will form. It's a basic cosmic recipe that seems to operate consistently throughout the known universe, from small moons to giant planets and potentially even distant stellar systems. These extraterrestrial auroras also help us better understand terrestrial auroras through systematic scientific comparisons. By studying how different magnetic field intensities, different atmospheric compositions, and different particle sources create different types of auroras, we develop a much deeper and more universal understanding of the fundamental physical processes involved. Future investigations of planetary auroras using advanced space telescopes and robotic missions may reveal auroras on extrasolar planets, offering precious clues about their magnetospheres, atmospheres, and potential habitability. Discovering auroras on distant worlds would be like finding universal luminous signatures of fundamental physical processes, confirming that we live in a universe where the same physical principles operate from subatomic to galactic scales. The study of auroras throughout the solar system has also revealed the incredible diversity of space environments. While Earth's auroras are powered primarily by solar-wind interactions, Jupiter's auroras receive significant energy from its volcanic moon Io, and Saturn's auroras are influenced by its icy rings and moons. This diversity shows us that auroral phenomena can arise from many different energy sources and configurations. Recent missions like NASA's Juno spacecraft at Jupiter and the Cassini mission at Saturn have provided unprecedented close-up observations of giant planet auroras, revealing complex structures and behaviors that continue to surprise scientists. These observations have shown that planetary auroras can be far more dynamic and variable than previously thought, with some lasting only minutes while others persist for months. Our human capacity to study, document, and understand aurora borealis has evolved in a truly revolutionary manner over the centuries, dramatically transforming from casual visual observations and purely poetic descriptions of the first Arctic explorers to a precision mathematical science that utilizes the most sophisticated and advanced technologies available to human civilization. This extraordinary technological evolution has not only exponentially expanded our detailed scientific knowledge but also completely democratized the aurora experience, allowing millions of people around the entire planet to share the transcendent beauty of this cosmic phenomenon. Imagine the first Arctic explorers and navigators of past centuries, equipped only with their human eyes and their limited capacity for verbal description, desperately trying to capture in inadequate words the absolutely transformative experience of witnessing an intense and spectacular aurora. Their historical descriptions, though often poetic, evocative, and emotionally powerful, were necessarily subjective, limited by human sensory perception, and incapable of revealing the quantitative and fundamental physical aspects of the phenomenon. Today, in dramatic contrast, we possess scientific instruments that can detect auroras completely invisible to the naked eye, measure their intensities with absolute mathematical precision, analyze their spectra with exceptional spectral resolution, and document events lasting only fractions of seconds. The scientific revolution historically began with the invention and application of photography to auroras. The first aurora photographs, laboriously captured in the late 19th century using extremely sensitive photographic plates and exposures of several minutes, were true simultaneous scientific and artistic milestones. They revealed geometric structures, spatial details, and temporal characteristics that the human eye simply couldn't perceive or memorize with precision, conclusively demonstrating that auroras possess three-dimensional and dynamic architectures, much more complex and organized than any visual observer had ever imagined. Have you ever thought how it must have been scientifically shocking and philosophically transformative for the first photographers to discover that their primitive cameras could literally see auroras that were completely invisible to direct visual perception? Modern digital aurora photography has become simultaneously a precise science and a sophisticated art form. Contemporary digital cameras equipped with highly sensitive CMOS or CCD sensors can capture extremely faint auroras in exposures of just a few seconds, revealing subtle colors, delicate structures, and temporal variations that would be absolutely impossible to perceive through direct visual observation. Specialized photographic techniques like high temporal resolution time-lapse and 360-degree panoramic photography create aurora representations that completely transcend the limited visual experience, showing complete temporal evolution and true spatial scale of these atmospheric phenomena. But the true scientific revolution came with the development and application of highly specialized and technologically sophisticated scientific instruments. High-resolution optical spectrometers mounted in terrestrial observatories can analyze aurora light with extraordinary spectral precision, identifying not only which specific gases are producing each observed color, but also determining their physical temperatures, movement velocities, numerical densities, and precise electronic excitation states. It's like having an advanced chemical laboratory that can chemically analyze atmospheric samples located hundreds of miles away without any direct physical contact. Radar systems constitute particularly powerful and revolutionary tools for studying auroras in ways completely impossible through optical methods. Incoherent scatter radars, enormous and technologically complex instruments, like the famous IceCat in Scandinavia, can directly measure the physical properties of auroral plasma, including electron density, in temperature, particle drift velocities, and local electric fields, all with temporal resolution of seconds and spatial resolution of miles. These sophisticated instruments have revealed that auroras are much more dynamic, structured, and physically complex plasma phenomena than their relatively simple visual appearances suggest. The space age brought a completely new and revolutionary observational perspective. Artificial satellites equipped with specialized imagers can photograph auroras from above, from a unique orbital perspective, revealing their true global extent, precise geographic organization, and spatial relationship with invisible structures in the magnetosphere. Spectacular images captured by the International Space Station show auroras as undulating green curtains seen from space, creating an aesthetic and scientific perspective that no terrestrial observer could ever directly experience. Have you ever wondered how we manage to scientifically study the individual microscopic particles that create auroras? Sophisticated particle detection instruments installed on scientific satellites can measure the kinetic energy, vector velocity, direction of movement, and even the atomic species of individual electrons and protons in Earth's magnetosphere. These quantitative data, when combined with simultaneous observations of resulting auroras, allow us to establish direct causal connections between microscopic processes and macroscopic manifestations on scales varying from nanometers to thousands of miles. Global networks of completely automated all-sky cameras, like the impressive Themis network in North America and the Miracle network in Scandinavia, capture complete celestial hemisphere images every few seconds, operating continuously 24 hours a day during the entire Arctic darkness season. These technological networks create dynamic real-time maps of auroral activity on a continental scale, allowing scientific study of phenomena that simultaneously extend over millions of square miles. Artificial intelligence and modern machine learning algorithms are dramatically revolutionizing auroral data analysis. Advanced computational systems can automatically identify different morphological types of auroras in tens of thousands of images, detect extremely subtle statistical patterns that would completely escape human analysis, and even predict the probabilistic evolution of auroral systems based on historical data analysis and real-time geomagnetic conditions. Mobile applications for smartphones have transformed ordinary citizens into a distributed global network of scientific observers. With automatic aurora forecast notifications, integrated cameras capable of high-quality nighttime photography, and GPS for precise geographic location, millions of people now regularly contribute to international scientific databases simply by sharing their personal observations, amateur photographs, and field experiences. Live streaming technology allows auroras to be observed in real time by people anywhere in the world. High-sensitivity cameras installed in privileged locations continuously broadcast the Arctic sky, completely democratizing the aurora experience and eliminating the geographic and economic barriers that previously limited their observation. Modern aurora research has also benefited from advances in space-based instrumentation. Satellites equipped with ultraviolet and X-ray detectors can observe auroras in wavelengths invisible to human eyes, revealing aspects of the phenomenon that ground-based observations miss. These space-based observations have shown that auroras extend much higher into the atmosphere than visible light suggests, and that they're accompanied by emissions across the entire electromagnetic spectrum. The development of sophisticated computer modeling has allowed scientists to create detailed simulations of aurora formation and behavior. These models can predict how auroras will respond to different solar wind conditions and help identify which physical processes are most important for different types of auroral displays. Advanced models now incorporate quantum mechanical effects, detailed atmospheric chemistry, and complex magnetosphere dynamics to provide increasingly accurate representations of auroral phenomena. Citizen science projects have revolutionized aurora research by engaging thousands of volunteers worldwide. Projects like Aurora Zoo allow ordinary people to classify aurora types in satellite images, contributing to large-scale statistical studies that would be impossible for professional scientists to complete alone. This democratization of scientific participation has led to new discoveries and insights that might otherwise have been missed. As our extraordinary journey through the scientific and poetic mysteries of Aurora Borealis approaches its natural conclusion, it's deeply appropriate and scientifically fascinating to turn our curious and speculative eyes toward the future. What will aurora science be like in the coming decades? What revolutionary discoveries and fundamental insights await dedicated scientists? And how might inevitable changes in our planet, solar system, and technological capabilities affect these celestial spectacles that so fascinate and inspire humanity? The future of auroral research is intimately and inexorably linked to extraordinary advances in cutting-edge space technology. Scientific space missions planned for the next decade include coordinated constellations of small miniaturized satellites, CubeSats and nanosatellites that will function collectively as a three-dimensional, distributed scientific laboratory in Earth's magnetosphere, simultaneously measuring physical conditions at dozens or hundreds of different points strategically scattered throughout near space. Imagine a sophisticated three-dimensional network of specialized sensors systematically spread throughout the space, surrounding Earth, creating dynamic real-time maps of how solar particles flow, accelerate, and interact with magnetic fields on scales varying from meters to millions of miles. One of the most intriguing and fundamental scientific questions that future research hopes to definitively resolve is the persistent problem of auroral acceleration. We know empirically that solar wind particles need to be accelerated to much higher energies than they possess when initially arriving at Earth's magnetosphere to create the brightest and most spectacular auroras. Where precisely and through what specific physical mechanisms this dramatic acceleration occurs remains one of the great unsolved mysteries of contemporary space physics. New space missions equipped with ultra-high temporal resolution instruments and unprecedented sensitivity will finally be able to directly capture these microscopic acceleration processes in action, resolving fundamental questions that have intrigued scientists for decades. Have you ever thought deeply about how global climate changes might paradoxically affect auroras in completely unexpected ways? Curiously, anthropogenic global warming may significantly alter conditions in the upper atmosphere in ways that potentially make auroras brighter, more intense, and more visible. The continued increase in CO concentrations in the upper atmosphere causes radiative cooling at these elevated altitudes, a counterbalancing effect to the warming of lower atmospheric layers, potentially intensifying the chemical reactions and physical processes that produce auroral light. It's a fascinating scientific irony. While we progressively warm the lower atmosphere through greenhouse gas emissions, we simultaneously cool the upper atmosphere, creating conditions potentially more favorable for intense and long-lasting auroras. The growing and exponential human space activity is creating new artificial phenomena that interact in unforeseen ways with natural auroral processes. Launches of extremely powerful rockets can temporarily create artificial auroras through injection of gases and particles into the upper atmosphere. And the growing population of artificial satellites in low orbits may subtly affect the natural electrical currents flowing in the ionosphere. We're rapidly entering a historical era where human technological activity in near space becomes a significant environmental factor that must be considered and modeled in aurora science. The emerging and interdisciplinary scientific field of auroral archaeology creatively uses diverse historical records, including ancient texts, artistic paintings, medieval chronicles, and even preserved oral traditions of Arctic indigenous peoples, to systematically reconstruct the history of auroral activity over centuries or potentially millennia. This interdisciplinary methodological approach may reveal long-term temporal patterns in solar activity and secular variations of Earth's magnetic field that aren't apparent in modern instrumental scientific records, which cover only the last few decades. Have you ever wondered if we might someday artificially and deliberately control auroras through advanced technology? Ambitious scientific experiments currently proposed include using extremely powerful radio transmitters to paint controlled auroras in the sky through selective and directed heating of specific ionospheric regions, creating geometrically organized and temporally controlled luminous patterns. Although still largely experimental and technically challenging, this futuristic technology may eventually have important practical applications in global communication, precision navigation, and even creating programmed auroral spectacles on demand for educational, scientific, or aesthetic purposes. Advanced artificial intelligence and deep learning algorithms are promising to revolutionize not only our ability to predict auroras with unprecedented precision, but also to interpret them as indicators of much broader physical processes. Future computational systems are being developed to automatically recognize extremely subtle patterns in auroral data that might precede seismic events, regional climate alterations, or even extreme solar activity days or weeks in advance. Auroras may become a sophisticated environmental diagnostic tool for the integrated general state of the Earth-Sun system. The future also promises a much deeper and more comprehensive understanding of auroras on other planets and distant stellar systems. The James Webb Space Telescope and future next-generation space observatories may eventually be able to directly detect auroras on extrasolar planets, offering precious scientific clues about their magnetospheres, atmospheric compositions, and potential habitability. Discovering auroras on worlds orbiting other stars would be like finding universal luminous signatures of fundamental physical processes, confirming that we live in a universe where similar phenomena operate on unimaginable cosmic scales. Robotic missions planned for Jupiter and Saturn's icy moons will study their auroras as indirect indicators of the presence and characteristics of subsurface oceans. Auroras on Europa, Enceladus, and other potentially habitable moons may reveal not only the structure and dynamics of these hidden oceans, but potentially even indirect signs of biological activity. If it exists in these extreme environments, direct human exploration of the solar system will create completely unprecedented scientific opportunities to study auroras from currently impossible perspectives. Astronauts on future lunar missions will be able to observe terrestrial auroras from a unique viewpoint in space, without any atmospheric interference, potentially revealing aspects of the phenomenon that have never been observed or documented. Future permanent lunar bases may serve as ideal platforms for specialized observatories, dedicated exclusively to studying dynamic Sun-Earth interactions. One of the most exciting possibilities is the eventual development of accessible space auroral tourism. Commercial suborbital flights already allow civilians to directly see Earth's curvature and experience the darkness of space. It's not scientifically far from the day when specialized space flights will be able to take privileged observers to the exact altitude of auroras, allowing them to literally fly through these curtains of cosmic light, experiencing auroras from a completely immersive perspective. Imagine the personally transformative experience of being physically immersed in an active aurora, three-dimensionally surrounded by luminous particles dancing around the observer in all directions. Earth's magnetic field itself is in constant change, and evidence suggests it may be gradually weakening, possibly moving toward a magnetic pole reversal. Such an event, which occurs every several 100,000 years, would dramatically alter global auroral patterns. During a reversal, auroras might appear at any latitude, creating light shows visible across the entire planet, but also exposing our atmosphere to increased solar radiation. The growing sophistication of computational models is bringing us closer to the ability to simulate auroras with perfect realism. These models not only help us understand the physical processes involved, but can also be used to create virtual reality experiences indistinguishable from real auroras. People anywhere in the world will be able to experience the sensation of standing beneath Aurora Borealis without leaving their homes. Citizen science will continue playing an increasingly important role in auroral research. Increasingly sophisticated mobile applications will transform millions of smartphones into aurora detectors, creating the largest monitoring network ever built. This democratization of scientific observation could lead to unexpected discoveries made by casual observers who capture rare or unique events. Future auroral research will also benefit from quantum sensors and other emerging technologies that can detect incredibly subtle changes in magnetic and electric fields. These ultra-sensitive instruments may reveal previously unknown aspects of auroral physics and potentially discover entirely new phenomena associated with these cosmic light displays. The development of space-based solar power systems and other large-scale space infrastructure may create new types of human-induced auroral phenomena. As humanity's presence in space grows, we may need to consider how our activities affect natural auroral processes and develop new categories of anthropogenic space weather. Advanced materials science may lead to the development of artificial auroral displays for terrestrial use, potentially allowing controlled recreation of auroral colors and movements for educational, entertainment, or therapeutic purposes. While these wouldn't be true auroras, they could help people around the world connect with and understand these cosmic phenomena. The integration of auroral science with other fields like atmospheric chemistry, climate science, and even biology may reveal unexpected connections. For instance, researchers are beginning to investigate whether auroral activity might influence weather patterns, ecosystem behaviors, or even human health in subtle ways that we're only now beginning to detect. And here we arrive, naturally and poetically, at the end of our extraordinary journey through the scientific and contemplative mysteries of Aurora Borealis. I want you to pause for a deep and reflective moment and carefully contemplate everything we've explored and discovered together during this special night we've shared. We began with you, perhaps comfortably settled in an intimate and welcoming place, imagining yourself transported to the vast frozen and silent plains of the Arctic. Now, after conceptually traveling millions of miles through outer space and cosmic time, we symbolically return to the starting point, but profoundly transformed by acquired knowledge and expanded understanding. Do you remember the fundamental question we asked at the beginning of this intellectual journey? How is an aurora borealis born? Now we know that the answer is an extraordinarily complex and beautiful cosmic symphony that harmoniously involves our magnetic star, our protective planet, and the most fundamental laws of physical nature. Each individual curtain of light that gracefully dances in the Arctic sky is simultaneously the final result of an intricate chain of events that began 93 million miles away, in the burning nuclear depths of the Sun, and the product of quantum processes that occur instantaneously on the subatomic scale. We discovered scientifically that auroras are born when electrically charged particles, accelerated in colossal nuclear energy explosions, undertake an epic journey of several days through the vacuum of interplanetary space, carrying with them colossal kinetic energy and precious information about our star. We learned how Earth's invisible but powerful magnetic shield, our protective magnetosphere, elegantly directs these cosmic particles toward the magnetic poles, where they penetrate our upper atmosphere through natural magnetic portals. We saw how, in the intimate and fundamental dance between microscopic particles from the cosmos and terrestrial atmospheric gas atoms, kinetic energy miraculously transforms into pure and colored light, painting the night sky with the characteristic and mathematically precise colors of each specific chemical element. Have you thought deeply about the poetic and scientific elegance of this extraordinary process? Each individual photon of auroral light that your eyes capture and your brain processes traveled an absolutely extraordinary and epic path. It was born in nuclear fusion reactions in the heart of the sun, crossed the vacuum of interplanetary space for millions of miles, navigated through complex terrestrial magnetic fields, precisely collided with a specific atom in the upper atmosphere, caused a quantum electronic transition, and finally reached you as a direct, luminous messenger of the fundamental cosmic interconnection that permeates the entire universe. But our intellectual and contemplative journey revealed much more than just the detailed physical mechanisms of auroras. We discovered that they are visible manifestations of something even deeper and philosophically significant: the fundamentally interconnected and interdependent nature of the cosmos. Auroras empirically demonstrate to us that there is no real separation between solid Earth and apparently empty space. We are literally an integral part of a dynamic and living system that extends harmoniously from our planets, molten core to the farthest reaches of the solar system and beyond. Through multidisciplinary scientific study of auroras, we touched on existential questions that completely transcend pure science and venture into the realms of philosophy, art, and spirituality. They speak eloquently to us about our unique position in the universe, about the extraordinary delicacy of physical and chemical equilibriums that make life possible, about the inherent mathematical beauty of fundamental physics laws. Each individual aurora is simultaneously a local phenomenon, specific light in the sky above a particular observer, and a cosmic event profoundly connected to universal rhythms of the solar system and galaxy. Have you wondered philosophically why auroras affect us so deeply on emotional and spiritual levels? Perhaps it's because they represent a rare and precious opportunity, when we can literally see the laws of physics in dynamic action, not confined in abstract mathematical equations or static computational graphs, but manifesting in all their visual glory, dancing majestically before our amazed eyes. They magically make the invisible visible, transforming intangible magnetic fields and imperceptible subatomic particles into celestial art of transcendent beauty. Auroras also teach us profound lessons about temporality and permanence, about the ephemeral and the eternal. Each specific aurora is absolutely unique and dramatically ephemeral, lasting only hours or minutes before silently fading into darkness. But the auroral phenomenon as a universal process is eternal and permanent. Auroras have danced continuously in polar skies for billions of years before life emerged on Earth, and will continue their cosmic dance long after our species has followed its own evolutionary path through time. There's something profoundly and universally human in our persistent fascination with auroras. They simultaneously awaken in us both the rigorous scientist and the sensitive poet, both the analytical technician and the contemplative mystic. They can be completely explained and understood by the most advanced modern physics, but this doesn't diminish in the slightest their transcendent power to inspire us, amaze us, transform us, and connect us with something greater than ourselves. It's perfectly possible to completely understand how an aurora works in scientific terms and still be moved to tears by its ineffable beauty and cosmic significance. Our exploration of auroras on other planets and moons revealed that we are privileged members of a much larger and more diverse cosmic family. Auroras are not an exclusive privilege of Earth. They dance magnificently in the skies of Jupiter, Saturn, Mars, and probably on unimaginably distant worlds orbiting other stars in remote galaxies. Every time we observe a terrestrial aurora, we're witnessing a truly universal phenomenon that connects our personal experience to the vast scales of the infinite cosmos. And perhaps most importantly, auroras constantly remind us that we live on an extraordinary and precious planet, silently protected by a magnetic shield that has worked tirelessly for billions of years. They are a constant visual reminder of the delicate fragility and unique preciousness of our cosmic home, a world that developed such specific, delicate, and improbable conditions that allowed the miraculous flourishing of complex life and reflective consciousness. As we naturally conclude our shared journey, I want to express my deepest and most sincere gratitude for accompanying me on this extraordinary exploration. Together, we conceptually traveled from the sun's nuclear depths to the confines of Earth's magnetosphere. We courageously dove into the quantum physics of excited atoms and emerged philosophically contemplating the future of auroras on distant and unknown worlds. It has been a genuine honor and privilege to share with you this harmonious dance between rigorous science and natural poetry, between precise technical knowledge and transcendent cosmic admiration. Now, when you look at the night sky, whether it's artificially polluted by urban lights or crystal clear and pristine, in a remote natural region, you'll carry with you a much deeper and richer understanding of the invisible but fundamental processes that constantly connect our Earth to the broader cosmos. And if someday you have the extraordinary good fortune to personally witness an aurora borealis in all its glory, you'll know that you're observing much more than simply a visual spectacle of colored lights, but a tangible and visible manifestation of the most fundamental forces that govern the entire known universe. Aurora borealis are born from an extraordinarily complex cosmic dance between particles, magnetic fields, and planetary atmospheres, but perhaps they're also born from something even deeper and more universal: the inherent cosmic tendency toward transcendent beauty, organized complexity, and fundamental connection between all things. They poetically remind us that we live in an extraordinary universe where the most rigorous science and the most sublime art naturally converge in phenomena of transcendent beauty and meaning. And now, one final contemplative question for you to carry with you on your continuing journey through life. If auroras are visible manifestations of fundamental cosmic interconnection, what other invisible but equally significant dances might be occurring silently around us at every moment, waiting only for us to develop the adequate scientific instruments or necessary perceptual sensitivity to recognize, understand, and celebrate them?